In this first question, okay, a student prepares 100 milliliters of a solution of potassium permanganate using 10 milligrams of potassium permanganate. So to get that concentration, we're going to use the moles over liters. Okay, so we're going to start off with 10 milligrams, and we're going to divide by the volume, which is 100 milliliters. And with the 10 milligrams, we can say there's 1,000 milligrams per gram. And we can use the molar mass, 158 grams per mole. And for every mole of KMnO4, then we're going to get 1 mole of MnO4 minus. And the last thing, this milliliters gets changed to liters in that step. So when we do all this, we get 6.33 times 10 to the minus 4 molar. So it's just a nice setup. Okay, the absorbance of this stuff. Okay, what happens is potassium permanganate, you just really ought to know, is purple. In fact, it's, depends on how much you dissolve, but it's very kind of a nice reddish purple. And the idea, looking at this chart, well, what's the color of the solution? Okay, it's going to be a purple, violet, kind of a, you might say, well, here's the purple side, here's the red side. Okay, but it's absorbing blue and green and yellow and all those colors. So since those colors are absorbed, the only ones we're going to see are the purple and red. And you can see that that is, is kind of a nice, reddish purple color. So if you were answering on the AP test purple or red, you'd be great. Now, the colorimeter that the student uses measures at these four wavelengths of light, and that's because there are 4 different LED lights in there. And the student decides to use 565. Is this the best choice? Yes, because if I look at those 4, the 635 is in the red region right here. Okay, the 565 is in the green region. The 470, that's in the blue region. And finally the 430, that's in the purple region. And you can see that what's happening is that this absorbs the best right here. Okay, way over here in the green region. Okay, so that's where it absorbs the best. That's the one you want to use for the experiment. Okay, at 565, the absorbance of the KMnO4 is found to be 0.8. The student transfers 5 milliliters into a test tube, adds 5 milliliters of water. So diluting it down by half, well, one of the big points here of the Beer's law is the fact that the absorbance and the concentration are proportional to each other. So if you take the concentration down by half, then you're also taking the absorbance down by half. So the answer should be 0.400, okay, for the absorbance. Okay, a student performs an experiment by adding some tin to chloride. Okay, well, KMnO4, one of its main uses is as an oxidizing agent. Okay, and so it's going to change from MnO4 into Mn2+ in an acidic solution. And it gets oxidized, so I mean it's getting reduced, so whatever's with it gets oxidized. So we're having tin in the 2+ turning into tin in the 4+. So we're going to do this as half reactions. So we'll start off and say Sn2+ turns into Sn4+. That's going to involve 2 electrons. And then on the second one here, we have the MnO4 minus turning into Mn2+. That's going to have 4 oxygens, so we're going to need 4 waters. And if you have 4 waters, we're going to end up with 8 hydrogens. But to make these 2, because this equation is going to have 2 electrons, and this equation, as we get down, are going to have 5 electrons, then we're going to multiply the top by 5, multiply the second one by 2. So then we come up with these 2 equations that are shown. Okay, so 5, 5, and 10. Bottom is 10, 16, 2, 2, and 8. So the 10 electrons, those cancel, and then the rest of the reaction is just written here. So the question, so first of all, do the balanced equation. Here it is here. And then how many electrons are transferred? Okay, 10 electrons are gained, 10 electrons are lost. Okay, it's 10 electrons are transferred. So don't get confused. Sometimes people add those and say 20 electrons, but it's the same 10 electrons being gained and lost. So it's only 10 electrons. Okay, student performs an experiment by observing the absorbance changes. So they're actually getting this data, okay, over time, and then they're calculating the natural logs and the 1 over constant absorbances. And then what happens is they graph them as well. So the job is you're saying, okay, the rate law depends only on the permanganate, so the other chemicals we just don't need to worry about. So what is the order of this permanganate and what's the rate law? Well, from these equations, we can see that the natural log versus time, okay, that's the one that is a straight line, so that tells us this is first order. If it was absorbance, which is proportional to concentration, so concentration versus time, this would be a zero order. If this one were a straight line, and if the 1 over the absorbance were a straight line, okay, it'd be second order. But it's not. It's the natural log of time versus time. That's the first order. So that means our rate law then is going to be rate equals K times MnO4 minus to the first order. Now we want to figure out the rate constant K. Well, in this time, we can't go back. Sometimes, you know, we would have a rate and we'd have a concentration from our data and we would just substitute it in, but we don't have that kind of data. We have this graphing sort of data. So we have to go back, and since we know that this is first order, then we can use the first order integrated rate law. Okay, and so it's going to be the ln of the concentration minus the ln of the concentration at time 0 equals negative K times T. We're going to solve for K. And luckily, we already have these other numbers here. We need the ln at time 0, and we have to pick any time. Let's say it's at 1. So ln at time 1, ln at time 0, so negative 0.72, negative 0.22. So that's where these two numbers come from, and that's at 1 second. So we substitute those in, work out the answer. We get 0.50 seconds to the minus 1. And again, you might notice, you've seen that before, for a first order reaction, the units are just, you know, inverse time. Now, what is the absorbance of the solution at 10 seconds? Well, then the similar thing, we're still going to use the integrated rate law. Okay, so we're looking for this value here, the A at 10 seconds. We know the time, ln of A at 0, we know it's the 0.22. We know the value of K, we know that T is 10 seconds. So we substitute all those in, get a number here, and then we have to kind of undo the natural log, so we take the E of both sides. So when we're done, we get 0.0054 as the absorbance at 10 seconds. Okay, the next question. Ascorbic acid, okay, which is vitamin C, is a weak acid, and it has an acid dissociation constant given. Write the expression for the reaction of the ascorbate ion in water. So the ascorbate ions, we're talking about something like, if I was talking about the acid HF, then we know that breaks up to be H plus and F minus, and that F minus is the conjugate base of the weak acid HF. And if I put that with water, okay, it would reform the acid and give me hydroxides. So that's what we're doing. Here's the ascorbate ion plus water. Okay, a proton, you know, leaves the water and comes over to the ascorbate, reforms ascorbic acid and leaves hydroxide. So that's that first equation. Now, write the expression for the base dissociation. So that's going to be products divided by reactants. Leave out the water because it's a liquid. So that's what we have here, products over reactants. And to get a value for that, we're just going to take Kw over Ka, and the Ka was given up here in the top, and we get 1.3 times 10 to the minus 10. Now we're saying we're going to have 200 milliliter solutions, okay, of 0.5 molar sodium ascorbate, and we want to know what's the pH of the solution. Well, the pH of the solution, that is going to go back and kind of be an icebox sort of problem. So we could go back here and make an icebox. We're not going to. It's a standard icebox. We've seen that before. We're starting with 0.500 molar and 0 and 0 minus x plus x plus x. We don't care about the water. Okay, so when we get all done and substitute it into this expression, we're going to have x squared over 0.5 minus x, and because this value here is so small, okay, that x is ignorable. So we just say 0.5 times 1.3 times 10 to the minus 10 equals x squared. All is said and done, we get a value for x, and x is our OH minus concentration because it's the value we're getting here in our OH. So we get 8 times 10 to the minus 6. Take the negative log of that, we get a POH, subtract from 14, and we get our pH. Now it says number 2, a 0.01 mole NaOH is added to beaker A. What's the pH of this solution? Well, this one takes a little thinking about, and the idea is we have in here a solution of sodium ascorbate, which is slightly, basic, 8.9, but we're going to put in a strong base. We're going to put in this NaOH. And it turns out that NaOH in solution is much, much more important than any little ascorbate ions that are floating around making things, So we're really, the pH is going to be due totally to the hydroxides that we put in solution. So we put in 0.01 moles over 0.1 liters, and so that's going to make it a 10 to the minus 1 molar solution of hydroxide. Take the negative log of that, we get the pOH is 1. Subtract from 14, we get the pH is 13. So just this by itself is 8.9. You put in a little bit of NaOH, okay, that takes over the base, and that's what you have. Now for the other beaker, beaker B, okay, we're going to put in some acid, okay, similar number of moles of acid, and the story here is totally different. So what happens is we have the ascorbate ion, but if we take the ascorbate ion and we add H pluses, it's going to turn it back into ascorbic acid. So we're going to have a solution where we have some ascorbate and some ascorbic acid, and we're going to have a buffer. So first off, we have to do an icebox just to do the stoichiometry. So if we do volume times molarity here and here, we can find out that the moles of ascorbic acid are 0.05. So we have 0.05 moles. We know from before that we're adding 0.01 moles of acid, H plus, and the Cl minus we don't care about. And, initially we have 0 ascorbic acid. And we can see what's going to happen. We're going to use up all of this. So this is minus 0.01 moles. This will be plus 0.01 moles, minus 0.01 moles. So when we're done, we have 0.04 moles of the ascorbate left over, and we have 0.01 moles of the ascorbic acid. So now we can go back and use the Henderson-Hasselbalch equation. So we know pH equals pKa plus the log of the concentration of the ascorbate over ascorbic acid. But, since these are together in the same solution, if you just use the ratio of the moles, that'll be just as good and save us a step. So we're going to use 0.01 over 0.04. Okay, there's a log of the Ka, 7.9 to 10 to the minus 5. So when all is said and done, we get a pH here of 3.50. So when we put the base in, the base made all the difference. We got a pH of 13.0. And when we put the acid in, okay, we had a reaction, and we ended up with a buffer with a pH of 3.50. Okay, the next part here. Vitamin C, okay, looking at the label, okay, this guy said it's buffered. Okay, it's buffered. So it has ascorbic acid and some sodium ascorbate. And it's really touted, that ascorbic acid is an acid. And if you eat too much acid, it's going to upset your stomach. And if you have things like, acid reflux disease and things, you say, well, I don't want to take vitamin C, that acid. So they make it into a buffer. And that way, then, it doesn't upset your stomach quite so much. Well, that's what they say. So here's a vitamin C. It says it's got 500 milligrams, which is about 8 times your daily requirement. But some people think that's really useful. And by the way, the daily requirement is how much do you need to keep from getting scurvy? And since that's not really a big problem around about now, but anyway, some people say that having lots of vitamin C is good. And vitamin C is one of those vitamins that, if you have too much of it, it just washes through your system anyway. So it's not a problem to take too much. So anyway, 500 milligrams is the ascorbic acid and ascorbate. Okay, we don't worry about the sodium, just the ascorbate and ascorbic acid. Then the sodium, okay, they say on, the nutritional labels that they have to tell you how much sodium is in there. So there's 23 milligrams of sodium. So we're going to use that little piece. We want to calculate the moles of ascorbic acid and the sodium ascorbate. If we know we have 23 milligrams of sodium, then we can go from milligrams to grams and molar mass, grams to moles. So we can find out how many moles of sodium, but those sodiums used to come from sodium ascorbate, So the moles of sodium must be the moles of sodium ascorbate. So that's a nice number there. Next, we're going to go ahead and take the mass of the ascorbate, because back here on the label, when they say that the vitamin C is ascorbic acid and ascorbate, they're really only talking about the ascorbate, not the sodium ascorbate, just the ascorbate. So that 0.001 moles, okay, we're going to count that as ascorbate, and then if we add up C6H7O6, then we get 175.116, and so we can find out how many grams of the ascorbate ion there is. And the reason we care about that is because we said we have 500 milligrams total of ascorbic acid and ascorbate, so we're going to subtract, this is 175 milligrams from our 500 milligrams, and so we can see that we have 0.325 grams of ascorbic acid, or 325 milligrams, but we're going to stick with grams. So now we've been able to find the grams, because we know the grams of ascorbate, and we know that the total is 500 milligrams of both, then we know how much ascorbic acid we have. Phew. Okay, now we just go back and say grams, change it to moles, so we can find out we have 0.00185 moles of ascorbic acid. So that was the two things we were trying to do, was find the moles of sodium ascorbate, and we used the 23 milligrams to get that. We found the mass and subtracted from the total mass, so we could get the moles of ascorbic acid. So we can see we have 0.001, 0.00185. So a little bit heavy on the ascorbic acid. So find the pH of this tablet. Okay, well, we can go back now and just use the Henderson-Hesselbach equation. And again, it's supposed to be concentration over concentration of the conjugate base over the acid, but these moles will work just fine. So we're going to say 0.001 of the ascorbate over 0.00185 of the ascorbic acid, and we have the log of the Ka. Okay, and so we end up with a pH of 3.84 for that. Now what happens if we have two tablets? Okay, now this is saying one tablet in 250 milliliters. It really makes no difference what volume we use, because it's the ratio of these two species, the weak acid and its conjugate base, is the ratio that determines the pH of this solution. So what happens here, if we were to use two tablets, we're still going to have the same ratio. So since that ratio doesn't change, then the pH will be the same in both cases. Okay, next, a second H can be removed. Okay, so and we have a Ka for that one. Well, that Ka, 1.6 times 10 to the minus 12, that's smaller than the Ka, or the first Ka that we had. So the first Ka was, I lost it. Okay, 7.9 times 10 to the minus 5. So we can see that this second one is not going to donate very well. Okay, so provide a quantitative explanation for why this reaction is ignored. Okay, well, what we're saying is we have a substance that can either gain a proton or lose a proton. Now, how much is it going to take for this guy to lose one more proton like it just did here? Well, this is the measure of that. That Ka of this second equation is the measure of how good it is as an acid. And if we go back and say, well, let's figure out the Kb of this same stuff, well, we have to do that by doing the Kw over the Ka, and we're going to use the Ka of the number we had on the other page. The 7.9 times 10 to the negative 5. So 1 times 10 to the minus 14 over 7.9 times 10 to the minus 5. We're going to get this 1.3 times 10 to the minus 10. That's the measure of how good this is as a base. And we can see that's not nearly so big. No, I mean, that is bigger. I'm sorry, that's bigger than the acid. So the question is, why do we ignore this second equation? Okay, because this has a very small tendency to, donate a proton. It actually works much better as a proton acceptor. Okay, so it's a stronger base than it is an acid. And again, we got that by calculating the Kb and finding the Ka, which is written up here on the page, and comparing those two. So it's a better base than it is an acid, so we don't have to worry about that second proton coming off. Okay, the next one here is talking about, consider a salt, okay, silver carbonate. It's got its Ksp. Okay, write the dissociation equation. Okay, the dissociation equation, it's simply silver carbonate solid turns into 2 Ag pluses and a CO3 2 minus, double arrow. And it's mostly this, okay, it doesn't break up very much. Calculate the molar solubility of this. Okay, well, if we were going to go back and do an icebox, and we say, let's say that S of this is going to break up, and this would be 0 and 0, then we're going to end up with 2S of silver, and we're going to add S of carbonate. When we go back and put it into our expression right here, then we're going to get 2S squared times S, and that equals the K. So, or we could say it's, 4S cubed equals the Ksp, and we go back and calculate S, 1.3 times 10 to the minus 4. That was the question. Now predict whether silver will increase, decrease, or remain the same when the following are added. So we want to go back to our equation here, okay, and we want to say, okay, let's do a Le Chatelier's principle. So silver chlorate, okay, well, chlorate is a spectator ion. What about silver? If I added some silver, it's going to shift my reaction this way, but I'm adding it, okay, I'm adding silver. So if I'm adding silver, then that's going to increase my silver ion concentration. Even if it shifts to the left, we're adding silver, so it's going to be up. What if I put in some HNO3? The NO3, we don't care about that. We're putting in H+. What if I put in some acid? Well, the acid is going to react with this carbonate, so that is going to make that go down. It's going to turn into CO2 and water. It's going to react with it, remove it from the equilibrium, so that will shift the equilibrium to the right, and that will increase the Ag+. Okay, so even though this one shifted to the left, it increased the Ag+ because we're adding Ag+, but the second one we are shifting to the right, and that would increase the Ag+. The last one, sodium carbonate. Okay, we don't care about the sodium, that's a spectator, but the carbonate, if we increase the carbonate ion concentration, it's going to shift things to the left, and if it shifts to the left, that's going to reduce our silver ion. So here we have silver ion going down, and that's what those three things are going to do. Okay, for this part here, this is one of these problems where it says, okay, a 1 liter solution contains some chloride and it contains some carbonate. So we're going to put in some silver nitrate. Again, we don't care about the nitrate, we just care about silver. Silver is added. Okay, which one is going to precipitate first? So what we need to do is calculate how much silver do we need in order to get a precipitate. So we have the expression, okay, for silver carbonate and for silver chloride. We know the value of the silver. No, we're going to calculate the silver because we know the value of the carbonate, we know the value of the chloride. Okay, so I'm going to go back here. So silver ion concentration squared times carbonate equals 8.1 times 10 to the negative 12. So we're saying that we want this silver, but we know that the carbonate, it says here, is 0.1. So if I put 0.1 in here, equals 8.1 times 10 to the minus 12, then I want to find x, which is squared, x squared. So what I'm going to do is divide both sides by 0.1, okay, and then take the square root of both sides. So my silver ion concentration equals, like we have it right here, equals the square root of 8.1 times 10 to the minus 12 divided by 0.1, which is 9 times 10 to the minus 6. So that is how much silver ion I need in order to start making a precipitate. Well, if I do silver chloride, okay, I have the similar situation. Okay, so I'm going to have the Ksp is equal to silver ion times chloride ion, and we know that that value is 1.6 times 10 to the negative 10. Sorry, this is so messy. But we know that the chloride is 0.1, so we want to find silver. So it's simply going to be 1.6 times 10 to the minus 10 divided by 0.1. So x is not going to be this value. This is actually wrong. Okay, it's not square rooted, so just ignore the square root part. It's one. Let me kind of clean that up. Okay, so this is good if we take away the square root part. Okay, so the answer is going to be 1.6 times 10 to the minus 9. 1.6 times 10 to the minus 9. And that is the silver ion concentration that we need in order to make a silver chloride. Well, which is smaller? Okay, this guy is smaller. So that's a smaller 10 to the minus 9 compared to 10 to the minus 6. So the silver chloride is going to precipitate first. Now the last part here, what's the value of the equilibrium constant? Okay, well, for this reaction, hopefully you recognize that this one could be put together using the two Ksp equations. Now the Ksp equations, you have to kind of know what that means. You know, just saying Ksp, you know it's solid turns into ion and ion for silver chloride, and solid turns into silver ions and carbonate for the silver carbonate. So looking at this equation, we can say, okay, here's silver carbonate on the right, but here it's on the left. So I'm going to have to take my silver carbonate number and flip it around. Okay, I'm going to flip the equation, and I'm going to inverse my K. So my K2, I want it 1 over my K2. Okay, my K1, it looks pretty good. The Ag plus is AgCl is on the left, but there's two of them. So that means I'm going to have to double this whole equation. And if I'm going to double it, that means I have to square the K1. So I want K1 squared times the inverse of 1 over K2. So the final answer is going to be K1 squared over K2. Okay, there's the math, and here's the answer. So again, hopefully you look at this equation and you recognize, oh, I could put this equation together by putting together the KSPs of those two equations. And when you do, you can see that the silvers are going to cancel out. You're going to have two silvers and you're going to have two silvers. That cancels out, but everything else stays and makes up this equation. So we have to multiply the two Ks. Okay, if we can add these two equations, we can multiply their Ks. And that's how we get that last answer. And that's the FRQ.